Everyone, so today we will be solving LeetCode 240. It's called Search a 2D Matrix Part 2. So the question is simple. We are given a 2D integer matrix and we need to write an efficient algorithm to find whether a given target value is present inside a matrix or not. So suppose we are given here 5. So indeed 5 is present. So that's why we return true. So also in the given matrix, we have two properties. So the first one being that each row in the matrix is sorted in ascending order from left to right. That means in a particular row, as we go rightwards, every time we would get higher values. And similarly for each column also. So as in a particular column, as we go downwards, we get higher values. That means every row and every column is sorted in ascending order. The row is sorting from left to right, and the column is sorted from top to bottom. So this was the problem statement. So it's very simple. I hope you got the problem statement. So the very naive solution would be very simple. It would be to traverse the entire matrix and explore all the elements. So since our size is matrix size is m cross n, so in the worst case we would explore all elements, that is m cross n elements. So our time complexity for the naive solution would become m cross n. But we need to write an efficient algorithm for this. So let's head over to the optimal approach of solving this. So heading over to the optimal approach, this is one of my personal favorite approaches. It's called staircase search. So in this approach, you would utilize the fact that all our rows are also sorted and all the columns are also sorted. So let me take one arbitrary starting cell. Suppose I took 8, and let's take a target value also. Suppose our target is 13. That is here. So, and our starting cell is, let me name it current. It has value 8. Now every time, so see, we see that our target is 13 and our starting value is 8. So our target is larger. That means we need to go towards that direction that yields me larger values. But you can see here, from 8, larger values can also be found at the right and at the bottom also. Because 9 is also larger than 8 and 12 is also larger than 8. So here we have two possibilities. Let me take another example. Suppose our starting value is 26. Again, our target is 13. So now our target is smaller. So that means we need to go in such a direction that yields me smaller values. But again, here you can see going left can also yield me smaller values, and going top can also yield me smaller values. So here also we have two possibilities. So you can see everywhere we have two possibilities. So that's why we get confused. See, going anywhere from among those two possibilities will definitely yield me 13. That is the target value. But I don't know which path would give me, would do that in minimum number of steps. And that's what I want because I want the efficient algorithm. And efficient would be that one which gives me the result in minimum number of steps. So that's why you can see every time we have two possibilities. So we are confused which part to choose. So what we do is here we would observe that there are two special cells. नीचे है उधर. So here we have two special cells. So the topmost right one and the bottommost left one are the ones which I'm talking about. So there's a special property of both of them that Suppose we can start with any one of them. Let's start with 15. So our current becomes 15. So what we would do is now let's compare. So our target is 13. So now we see that our target is lesser. So we need to go in that direction which yields me lesser values. Now you can see one beautiful thing that only there is one direction that yields me lesser values. See, if I went downwards, I would get 19, which is larger than current, right? Which you don't want. We want lesser values because our target is lesser. So we go towards left. So we reach 11. So now our new current becomes 11. So our current becomes 11 and target is 13. Now let's again do the comparison. Now our target is greater. So now you can see left going left would yield me smaller value, but going downwards would yield me higher values. So we go downwards and we reach 12. So now our current becomes 12. So current is 12 and target is 13. Again, target is larger. So we again need to go in that direction, which yields me larger values. So as you have already observed till now that going left is giving me smaller values and going down is giving me larger values. So here also we do the same. We go downwards because left would give me less value. But our target is larger, that's why we went downwards. So we reach 16. So now our current becomes 16 and our target is 13. Now again we do the comparison. Now our target is lesser. So if I go downwards, I would get larger value, which I don't want. So we go leftwards. So we get 9, right? So our current becomes 9. Also, one more thing. Suppose when I was at 12, you might wonder that we were searching for 13, right? So larger is also present at right. Why didn't we go to 19? So we didn't do that because see, we in the earlier step we came from right only, right? We came from right to left. That means the entire right column didn't have a target. That's why only we moved left in the previous step. So I hope this thing is clear. That's why we don't move right here again because we are already coming from right. So again, there's no point of going again in the same column, which we have already seen. So this is the point, and this is the reason why I didn't went towards 19 from 12. So I hope this is clear. So now our current becomes 9 and target is 13. Now our target is greater. So we know greater is always at the down. So we get 14. So our current is 14 now and target is 13. Now target is lesser and we know lesser we get in the left direction. So we go towards left and indeed we get 13, which is our target. So we return true in this case. So this was the staircase search solution. So let me explain the code of it and then discuss the time complexity of it. So heading over to the code. So we initialize this I denotes the row number of the starting cell and J is the column number. So you can see here that we started from here, right? Coordinates of this is 0, comma 4. So 0 means we were at 0th row and last column. So that's why I wrote here I is 0, that is first row, and J is matrix 0 dot length minus 1. That means last column. So this is the initialization of our starting cell's coordinates. Now, see, as I discussed that every time we are going to left or down, right? So what happens is by every time we are going either left or down, right? So every time if I go left, there may come a case when I even our j becomes less than 0. That means j becomes minus 1. So this is not possible, right? Otherwise it would give me r index out of bounds. So J, that is a column, should always be greater than equal to 0. And this is for left. And also we are every time going down also. So it may be possible that by going down every time, it may be we may come across a case that we go beyond our last row. That is, we also should put a check that I should be less than the number of rows. So these two checks we would put in the while condition. So that's why I wrote these two conditions, that we would continue our process and our search until these two conditions are met. So I hope this condition is clear. Then the thing is simple. This matrix of ij is nothing but a current cell's value. If it is equal to target, we simply return true. Otherwise, if our target is greater, so as I discussed in the case where our target was greater, we move downwards. So downwards means we need to increase our row number. Suppose you were at this row and we need to go to this row. So we need to increase the row number. Then only we can go to the lower row, right? So that's why if our target is greater, that means we need to go bottom. So that's why I increase the row number. Otherwise, if our target is lesser, that means we need less values, and less values, for less values, as I told you, we go leftwards. So leftward means going towards the left column. So we would decrease the column number. So that's why J minus minus. So it continue this. If our target would be present in the middle, you would anyways return true. And if the entire loop ends and still we didn't return true, so at end we return false. That means we couldn't find our target value in the matrix. So this was the code of it. Coming to the time and space complexity. So space complexity is simple. We didn't use any additional space, so it's big of 1. The time complexity is good. So let me derive that for you. So as you can see here, in the worst, let's consider the worst case, because when we talk about complexity, we always talk about worst complexity, worst case scenario. So if I started here, right? So our worst case would be if our target is this. So in it can be there can be multiple ways to reach this. Either we can go here, or we can follow this path, or any which ways we can follow this path. Any which ways we take, there is one thing common in every each one of them. That is, every time we performed n number of left moves. That is the number of columns we have. So every time we did n left moves. See, either we can do it previously or later. But any which ways, at the end, we would go n times leftwards. Then only we can reach here, right? From here. So या तो हम ये पाथ फॉलो करें या ये करें या फिर ये करें, कोई भी पाथ फॉलो करें, अल्टीमेटली हम n टाइम्स लेफ्टवर्ड्स तो जाएंगे ही, तभी हम यहाँ रोज इस कॉलम से इस कॉलम पे आ पाएंगे, राइट? सिमिलरली फॉर द बॉटम केस ऑल्सो, चाहे हम ये पाथ फॉलो करें, चाहे ये पाथ फॉलो करें, कोई भी पाथ फॉलो करें, सिंस हम यहाँ से यहाँ आ रहे हैं, at the end we would have covered m number of, that is the number of rows we have, m number of bottom moves. So in the worst case, the total moves become the bottom moves plus the left moves, which is m plus n. So this is the time complexity of a staircase search. So our time complexity of staircase search becomes big O of m plus n. So this is the time and space complexity of our staircase solution. So I hope this is clear, and I hope you understood the code and liked the approach. So yeah, this was it for today's video. Thank you so much.